problems with it. Right. So we'll probably be able to get through the last of 4.3 today. We did graph traversal, tree traversal, reverse Polish notation on Tuesday. We want to finish searching algorithms, sorting algorithms, and optimization algorithms today. We'll start with searching, although I pretty much covered these as part of the last one, but we'll have a look anyway. Yeah, we'll go through the presentation just because I spent a while making it, but honestly, I think most of you get this stuff. Right, so we need to know 3 algorithms for searching for things. This is searching through just a list or an array rather than a tree or anything as complex as that. So let's say that's our list. We've got Bob, Eve, David, Ellie, Siraj, Barry, Charles, Prina and Jerry in a list. And all we want to do is find if someone is in a list. We want to go to scan through that list and see if someone is there or not. Okay, so I want to find out, is Charles in that list? So a couple of approaches we could take to it. The most obvious one is a linear search. In a linear search, we start at the top and we check every element until it's either found or until we reach the last element of the list. That way we know for certain whether or not it's in there. So yeah, so we start at the top. Is that Charles? No. Is that Charles? No. Is that Charles? No. Is that? Is that? Is that? Is that? Yes it is. There we are, we've found it. And that's, there's a fault with the animation there, that's how a linear search works. Okay? It's a very simple system, very straightforward, but it has an issue. It's, if you remember big O notation from a couple of lessons ago, a linear search is order of n. It's a linear increase. So that means the speed of operation increases with the size of the list. So if there's 20 elements in the list, in the worst case scenario, it will take 20 comparisons before we know it's there. Because if it's not there, we have to go through all 20 to establish that. If there's 100 elements in the list, it'll take 100 operations. If there's a million elements in the list, it'll take a million operations. So as the list gets bigger, it increases the length of time. It's only order of n, it's nowhere close to intractable, but it will take more time the bigger it gets. A better search algorithm is a binary search. In a binary search, we always check the middle value. For this to work, the data has to be ordered in some fashion. We have to be able to know whether the item we're searching for is above or below the item we're currently looking at. If we can do that, then we can do a binary search and eliminate half the list every single comparison. So let's see how binary search works. So in this one, again, we're going to look for Charles. I've reordered them this time so they're in alphabetical order. So B for Bob is at the top, S for Siraj is at the bottom. So we go in at the middle. So we say, does Ellie equal Charles? No, it doesn't. But this time, rather than just going to the next one, we say, well, Charles, C, is lower down the list than E. So we know that Ellie, Eve, Jerry, Prina, Siraj, so 4 through to 8, we know it can't be any of those. So in one step, we can eliminate all those values. And then we repeat the next step. So again, we go in at the middle. In this case, there isn't an exact middle, so arbitrarily we go either above or below the middle. As long as you're consistent, as long as it's always the same, this will work. So in this case, I'm going above, so I've rounded down. So I'm saying, is Barry Charles? No, it's not. So Charles is above Barry in the list, so I can eliminate everything Barry and below. So now these are the only ones left. So going in the middle, is it Charles? Yes, it is. So that's a fantastic system, and this is order of log n. It's order of log n because each time you do a search, you eliminate half of the list. So if I doubled the size of this list, it would only take me one extra step, because in that one step I would eliminate half and I'd be back down to the size I was. So I could double it again. So if I doubled it twice and multiplied the size of the list by 4, it would be 2 extra steps. Multiply the size of the list by 8, it would be 1 extra step. So to give an indication of how much more efficient a binary search is, 1,000,000 values can be searched in 20 steps. So in other words, if you take 1,000,000 and you halve it 20 times, you'll get down to 1. It only works when the data is sorted, numerically or alphabetically. That's the downside to it. So if it's unsorted, the only option you've really got is a linear search. So if you've got a million unsorted values, it's going to take a million steps to find out if something's in there. If you've got a million ordered values, it can take 20 steps to find out if something's in there by doing a binary search. Okay, if you've got any questions about linear or binary search, quickly post them in there. So it's a 5-second lag, so I'll wait. So Ed looks angry. Why are you angry, Ed? I'll wait 5 seconds for the reply. Dylan's dabbing, but that's to be expected. I'm still not sure why Ed's angry. If everyone's okay with linear and binary searches, I know why Jack's angry. Jack's just an angry young man. Right, so if anyone's happy with linear and binary searches, we'll move on. There's a task they can have a go at. So if you remember the guess the number game, so I'm sure we've, actually no, at GCSE we looked at that one, but I'm sure you've all heard of it. It's the idea is you guess a number between 0 and 100, and each time you're told if it's correct, too high or too low. So if you were to do this properly with a binary search methodology, how many guesses will it take before you can guarantee you found the number? Okay? So you've got to guess a number between 0 and 100. You're going to take the binary search methodology, so your first guess will be 50. If it says too high, your next guess will be 25, etc. How many guesses can it take before you can guarantee you will have found the number? Post your guesses in the comments. Oh, and don't forget to like and subscribe. Apparently that's what you say on YouTube. People going for 7? It is 7. It is. If you take 100 and halve it, you get to 50, halve it again, 25, halve it again, 12 and a half. Keep doing that. You'll get down to one value after 7 halves. So that means that after 7 guesses, there's only one value left it could be. So yeah, you'd get it in 7. So a summary, for those of you that are making notes or need summaries for it. The advantages of a linear search is it's a simple algorithm and it works on any list. But the disadvantage is it's slow on large lists. A binary search is very fast on large lists. In fact, the larger the list gets, the more efficient it becomes. That's the nature of order of log n algorithms. The disadvantage is it only works if the data is sorted, so it can't be used everywhere. So as we looked at a couple of lessons ago when we were looking at trees, a sort of hybrid way, a way of being able to do a binary search methodology without having to have a sorted list is a binary search tree. In a binary search tree, rather than just adding things to a list as we get these values, we stick them into a binary tree. I think I've been through this again. Yeah, I have. So Bob is this is as a list arrives. You don't take the list and put it into a tree. That's as slow as sorting it. But if as we're getting these values we put them into a tree to begin with, this can be a lot faster. So Bob comes in, goes at the root of the tree. Eve comes in, is placed in the tree, comes after Bob, so it's placed in the right subtree. David comes after Bob, so it's placed in the right subtree, but before Eve, so it's placed in the left subtree. Ellie, after Bob, before Eve, after David. Siraj, after Bob and after Eve. Barry, before Bob. Charles is after Bob, before Eve, before David. And Prina, and Jerry. And we end up with a tree like that. So if that's how our data is stored, now, fancy transition. So that's how our data's stored. We can now search that using an order of log n system. So if I want to find Jerry, I check Bob. Jerry is bigger than Bob, so I then check Eve. It's bigger than Eve, so I check Siraj. It's less than Siraj, so I check Preena. It's less than Preena, and there it is. And I can work down that one. So in other words, it would take 1, 2, 3, 4, 5 steps, rather than all of them, which it would be in a linear search. But it's not guaranteed to be as good as a binary search, because if you get lucky and as the data comes in it ends up being a perfect tree, then yes, it will be as good as a binary search. If you get really unlucky, it'll be every bit as bad as a linear search. Realistically, it'll be something like this, quite close to a binary search. So we went through the tree search a couple of lessons ago, and you seemed all okay with it. We're still all okay with binary tree search. So those are the three searching algorithms we need to know. A recursive algorithm for adding value to binary search tree function looks like this. I think I did that last time. I'm skipping over most of the programming stuff because I'm aware that a few of you don't have access to programming stuff, and once we're back we'll focus more heavily on the programming if we get most of the theory out of the way during the lockdown. So program related stuff I'm skipping over. I'm focusing more on the raw theory. Okay. Welcome, Toby. You've got a nice new sparkly account. Right. Oh, that's the same one we did last time. We don't need to do that again. That's all we've done. Yeah. Okay. So those are that. Because most of that stuff we've done before, I'm going to just carry on to the next thing. If you've got any questions about searching algorithms, please post them quickly. But generally that stuff everyone's done. It's part of most of the GCSE specifications, and we looked at binary tree search a couple of lessons ago, so we don't need to spend that much time on it. So that's searching. So as we can see clearly from searching, if we can, we want to be able to do a binary search, because a binary search is going to be lightning fast no matter how big the thing gets. Angry again, Ed. Does that mean you're not sure about something? You need to know linear search is order of n. Linear, it goes up linearly with the size of the list. Binary search and binary tree search are both order of log n. In other words, as you double the size of the list, it generally increases the number of searches by 1. So it gets more efficient the bigger it gets. There's two sorting algorithms we need to know. So the question becomes, well, what's going to be more efficient? If I've got an unordered list, yeah, I think he is, and it's a bit early in the morning for him. He's sat in the chair. He has to type like this because all desks are too high for him, and he just gets really angry. Okay. There's so it becomes a question of which is more efficient. If we've got an unordered list, is it better off that we just do a linear search and it's accept that it's order of n, or do we sort it to make it ordered so that we can do order of log n? Well, how do we sort it? Here's a couple of sorting algorithms. Are there any sorting algorithms that are efficient enough that sorting and then binary searching is going to be better than linear searching? Well, let's investigate this one. We only have to know two sorting algorithms. If you're interested in this, do a bit of research. There are loads of sorting algorithms, and most of them are quite interesting to find out how they go. They're quite easy to understand. We only need to know two. We need to know one that's very inefficient to see how inefficient it can get, and one that's very efficient so that we can see that. So sodium chloride said merge and binary is going to be better than linear. Well, let's find out if you're right. I don't know who sodium chloride is, but yeah, we'll see if you're right. Well, first of all, let's look at bubble sort. Again, if you did the Educast GCSE, which is everyone from Catmus, we have done bubble sort and merge sort. Those that did OCR, which I think is everyone else, have you guys done bubble sort and merge sort? Do we know what they are? So anyone that wasn't at Catmus, could you just post if you've seen a merge sort and bubble sort before? Okay. Okay, we're getting there. However, there are 2 Johns in the class, so a little bit closer. Yeah. So you guys have looked at this. So again, it'll be a quick recap. I'll just demonstrate to you. There is a video here on sorting algorithms that explains. There's a guy with cups explaining merge sort quite well, but I'll just do it on this and then we'll move on. Okay. Right, so for bubble sort, okay, a very easy sort to implement algorithmically, very easy to understand, but really inefficient, and rapidly becomes unusable. So if we have some values that are not sorted, so I'll just do these with numbers. So let's say we've got 5, 3, 1, 4, and 2. Okay. Yeah, I think it is. It works nice. I'll have to find out ways to do a register and that sort of thing, so I have to just call out and people write if they're there. That's the best I can do with that one. But yeah, so far this is working a lot nicer. Not sure why Teams gets it so wrong. There is a way to do Teams live stream like this, but it has about a 30-second delay, whereas YouTube's got it down to 5, so I guess this is the one we're doing. Yeah, you remember it, Jonathan. So what we have to do is we start here and we compare 2 values. So first of all, I compare those, and we swap them if necessary. In this case, we do need to swap them. So this becomes 3, 5, 1, 4, 2. We then move on and do the next comparison. So I check those 2. Do we need to swap those? Yes, we do. So that becomes 3, 1, 5, 4, 2. Then we check this one. Do we need to swap it? Yes, we do. 3, 1, 4, 5, 2. And finally, we swap that, and that does need swapping. So 3, 1, 4, 2, 5. Okay, and that's the end of the first pass. By the end of the first pass, what will have happened is the biggest number, wherever it is, will have bubbled up to the end. It's where the name bubble sort comes from. So the one thing we can know at this point is that that one will be in the correct position. We can't know the rest. Sometimes you'll get lucky and some of them will be in the right point, but we don't know that. So we have to do another pass. So next time round, these 2 need swapping. Yes, so that becomes 1, 3, 4, 2, and 5 we already know is correct. Then we have to swap these 2. Those are already correct, so no more is needed. So we do these 2. That does need swapping, so 1, 3, 2, 4, 5. And we know those 2 will already be correct because that was already in the right place. So we now know at the end of the second pass, those 2 are correct. So we do a third pass, which will leave us with 1, 2, 3, 4, 5. At this point, those are correct. We know that. Those 2 might be, and in this case are, but we don't know for certain, so we still have to do another pass to check. And we don't need to swap those, and 1, 2, 3, 4, 5 is our final order. Now this is phenomenally inefficient, because let's think about how many passes, how many steps it would take, and how that increases as they get bigger. So what I have to do that comparison, that comparison, that comparison, that comparison. 1, 2, 3, 4 comparisons for each pass. 4 checks, and I would have to do 4 passes in order to be certain they're in order. So it's 4 checks times 4 passes. So I have to do 4 checks 4 times. So in other words, 16 steps are needed to bubble sort 5 values. In other words, if n is my number of values, it turns out to be n minus 1 squared checks are going to be needed. And that squared is where the problem comes from. Because if I add one more to it, I'm going up with the square of the size of the list, not linear with it. So a bubble sort is order of n squared. Still not intractable. It has to be 2 to the n or above to be intractable. This is still manageable, but there will be a slowdown as the size gets bigger. And as the size gets bigger, the slowdown will become bigger than the previous slowdown. So the slowdown accelerates. It's not good. Yeah, so if there's a large number of things to be sorted, a bubble sort will really struggle. And as that gets bigger, it will struggle more and more. So as you get to the point where it starts to slow down, you add one more to it, the slowdown increases with the square of the size, so it gets worse. So bubble sort, algorithmically very easy to implement. You can do it with a nested for loop and one variable, but not efficient. Okay, so that's that one. I'm just going to tell us to save before I do a new one in case anyone wants to see it again. Not just saved internally? Yeah, whatever. No one's going to need to see that. So the next one we look at is something called a merge sort. Now, a merge sort is something that is very efficient and does do well with large data types. With large data sets. In a merge sort, we rely on two steps. This is something we refer to as a divide and conquer. The first step involves splitting it up into smaller lists. The second step involves merging those lists. So I'll look at those two algorithms separately. So this is how we can merge two sorted lists into another list. We need to know this in order to apply it in a merge sort. So let's say I've got a sorted list. One, 4, 6 and 9. I'm just about to tell it's a 4. And another list here, which is also sorted. Oh dear. 1, 3, 7 and 8. Okay, so if I have two lists that are already sorted, there is an algorithm to merge them together into a bigger list. Really easy to do. All you do is in a new list, you compare the top two. That's all. So I ignore everything else, I just compare top two. So I'm comparing 1 and 2. The smallest of that is 1, so that is removed from this list and goes into the new list. Then I repeat, I just keep doing that. So the second step is I compare the top two. So now I'm comparing 4 and 2. The smallest of that is 2, so that goes into that list and taken out of here. Then I compare the top two. So this time I'm comparing 3 and 4. So 3 goes into here and is removed from there. Then I compare the top two, 4 and 7. So 4 goes into here, is removed from there. Top two are now 6 and 7. So 6 goes into there and is removed. The top two is 7 and 9. So 7 goes in and is removed. The top two are 8 and 9. 8 goes in and is removed. And 9 is left, so 9 goes in. So now I've got all those values merged into another list that is also sorted. So that's a useful one. And that algorithm there is order of n. So just the merge part is order of n, because I have to do a comparison for every value that's in there. So if there are 10 values in total, I have to do 10 comparisons. If there are 20 values in total, I have to do 20 comparisons. So the merge part is order of n. So the divide part, the part that comes before we're merging, is we need to get to a point where we can start merging lists that are sorted. So if I've got an unsorted list, so I'm trying to do a merge sort on this data, something like that, that's not sorted. So I can't start merging it. So what I have to do is split it. So I split it in half, and then in half again, and then in half again, until I end up with lists that only have one value in. So if I've got this time I've got multiple lists. So a list containing 5, a list containing 3, a separate list containing 6, a list containing 9, a list containing 2. Let's see what that's meant to be. That's a 6, isn't it? List containing 2. Now I can consider those lists to be sorted. There's only one value in them. It's not possible for them to be unsorted. So now I've got 5 separate lists, I can start applying these mergers. That's easy, that's just one step to do that. So what we do is see how many times do I need to apply this order of n thing. Now if I have to apply it n times, then that's going to be n squared and I'm no better than a merge sort. But luckily it isn't. It's less than that. So if I, first of all, I'm going to apply the merge sort algorithm to 5 and 3. So 3 is lower than 5, so that goes in first and is removed from this list. 5 is the only one left, so that goes in there and is removed from this list. So now I have a list that's sorted 10, 3 and 5. Do the same here. I've got 6 and 9, so 6 is lowest, so that goes in first. Then 9 is left, so that goes in. And this one here has nothing to merge with, so that's just going to go there. Okay? So I've had to do at this point two mergers. I'll keep track of how many mergers I've had to do. So I've had to do 2 mergers. So let's do another pass through. So this time we'll do the merge algorithm on these. So check the top 2, 3 and 6. 3 is the lowest, so 3 goes in. Then check these 2, 5 and 6. 5 is the lowest, so 5 goes in, then 6, then 9. I'm left with this, and this one here is still left by itself, so I'll just do one merge on that to link them together. So 2 is the lowest, then 3, 5, 6, 9. So I ended up doing, in fact, if we'd ignored that 2 completely and started with a nice round number for it, I'd done 2 mergers, then 3. So I hadn't done n mergers. In fact, if we expanded that to have 8 values in it, after the first step there'd be 4, after the next step there'd be 2, then 1. So that would happen in 4 steps. So the merge part of it, the joining the list, the splitting the lists up and putting them back together, that is order of log n, because after each step we have half the number of lists that we had before, just like in a merge sort where you have half the number of things to search that we had before. Okay? So this means this whole total algorithm, the putting back together step is order of log n, and the merge thing that we have to happen on each of those order of log n ones is order of n. So this is called order of n log n, and we did look at that one when we did those. So it's less efficient than linear, but as it gets bigger, its efficiency gets closer and closer to linear. If I drew the graph of it, and this starts to look like a really messy screen, so if this is linear going up like that, and order of log n does that, which is terrific. Order of n log n does this and comes back towards linear. Never reaches it, but comes back towards it. So it gets more and more efficient as it gets bigger, but is always slightly less efficient than n. But compared to order of n squared, which goes like this and disappears off there, it's much better. So a merge sort is order of n log n. Not as good as... Ooh. Is this... Has this died? Is my internet down? As it says it's buffering on my screen. Are we still there? Is it still working? That's weird. What's happened? That seems to be alright. Yeah, seems to be back. It buffered on mine, but it seems to be alright. Okay. So if we go back to here, the things you need to know about it is how to do both of those things. You might be asked to step through them. So you need to know how to trace and analyse the time complexity bubble sort. In other words, it's order of n squared, because each time you increase it, you have to do an extra pass, and each of those passes includes n swaps. So you have to do n passes of n swaps, so n times n, so it goes up n squared. Hopefully that makes some sense. In a merge sort, because the merge part is linear, is order of n, but the amount of times you have to apply that merge is going up with log n, because each time you do it there's half the number of lists than there was before. It's order of n log n, which is more efficient. So any questions on sorting algorithms? Okay, you guys can stop rowing amongst yourselves for a second. Any questions on sorting algorithms? Right, so far, especially, I know certainly for those of you that did the Educast GCSE, everything we covered there was actually covered as part of GCSE, except for binary tree search. Binary search and linear search and bubble sort and merge sort were all part of the GCSE. Binary search we already did 2 lessons ago as part of binary trees, so nothing so far should be completely new for anyone. This should be just a recap. The last thing we need to do to finish this unit, and then what we'll do is next lesson we'll do an end of unit test on all of those 2 units. I'll give some past questions and mark them, is an optimization algorithm. Most of you already do maths, and I know Dijkstra's shortest path algorithm is part of the maths A level, but I don't know if you've got there yet. Has anyone done Dijkstra's shortest path algorithm in maths? I'll wait 5 seconds to reply, thanks to this annoying lag. Okay, so Dijkstra's has been covered by further maths, not been done in regular maths. Okay, right. Oh gosh, I always struggle with Dijkstra's because the only time I ever do Dijkstra's is in this one lesson once a year, and it's painfully complicated to do, and we don't spend that much time on it because this is where it gets a bit weird. It says understand and be able to trace Dijkstra's shortest path algorithm and be aware of the implications of a shortest path algorithm. But then it says in additional information, students will not be expected to recall the steps in Dijkstra's shortest path algorithm. That's weird. So that's almost implying you don't need to know it. The only thing I can imagine they can do is give you the algorithm for Dijkstra's shortest path and then ask you to step through it or do a trace table on it or something like that. So you don't have to have memorised Dijkstra's shortest path. You need to know what it is, you need to be able to work with it if you're given it, and you need to be able to state the pros and cons of it, but you don't have to memorise it. Okay. So, yeah, at this stage I'm not going to try and step through it because the video I found does explain it considerably better than I ever manage anyway. There's a link to it there, there's a video about it here. What I do say is the purpose of a shortest path algorithm is if you've got a graph, so if you've got a graph something like this, and you want to get from point A to point Z, the shortest path algorithm is an algorithm for working out, and these are weighted graph rather, so this is say 5, well that's 2, not 5, well 2, 5, 3, 1, 9, 6, 4. The shortest path algorithm is an algorithm that will work out the lowest value path from there, so it will analyse these and come up with, going from 2 to 1 is the going from here, let's do a different colour, going from here to here, then here to here, is the shortest path across that particular graph. That's all it does. It doesn't do this, the brute force method we talked about with the travelling salesman. It doesn't analyse every possible route and decide that that is the shortest one of all of them, that would be an order of n factorial problem. It would be utterly intractable. It has a nicer way of doing it. So what I suggest you do is you watch the video. There's no point me streaming a YouTube video over a YouTube stream. So what I suggest you do is watch that video on it and try and get the hang of it that way. It's a really nice explanation. It's how I learnt about it, and hopefully it'll make some sense to you, this research on that one. So in terms of what we're covering, that's it for this one. We've covered graph traversal, tree traversal, reverse Polish notation, searching algorithms, sorting algorithms, and you're going to watch a video on optimization algorithms, which is just Dijkstra's. It's something you need to know. So if we go back to this part, we've now filled all of 2 and 3. And what I'm going to do, I'm going to do an assessment point on those two combined. Do an assessment point on those two combined. So I'll give some, and the way I think I'm going to do this, on Tuesday's lesson next week, I'm going to, at the start of the lesson, I'm going to make the assessment point available. I'm going to ask you to do it and submit it. So if you've got a printer, you can print it and fill it on that. If not, you can just read off the screen, write the answer on a bit of paper, photograph it and send it to me, or type the answers up or whatever. So I'm going to set a fixed amount of time, make that available, you do it, send the answers to me, I'll then mark them. That's the approach we're going to take for it. It's the closest we can get to doing a proper assessment point, but it's going to be on those two. So we've got a while now, we've got about 45 minutes. I'm happy to quickly recap these, or if you want to look through 4.2, all of this stuff, and 4.3, all of this stuff, and post in the comments any questions you've got that you want me to answer, or any parts you'd like to look at again, then we'll do some revision of 4.2 and 4.3, and then we'll do an assessment point on it next lesson. So what would you like